Hello, and thank you for joining us. I'm Nicola St Clair.
And I'm Paul Deering.
And we produce Autotechnician magazine, providing independent workshop owners and technicians with job-useful, practical advice on how to boost revenue, find faults faster, and to support best practice.
It's more important than ever these days to keep up to date with the latest industry, technical and product news. Autotechnician provides this via print, web, digitally and social media.
With the help of independent trainers and sponsors, we also provide free online assessments so that technicians can benchmark their knowledge when it comes to diagnosing faults. It takes just a few moments to register for Autotech at www.autotechnician.co.uk/registration. You will then have free access to the multiple choice assessments. There are currently 9 to choose from, with more to come next year. Once completed, you'll instantly receive your score and explanations of the topics covered. We have met many of you at our Big Day Out technical training events, which we've sadly had to postpone this year. All things being well, we will hold a technical live event in 2021.
You can register your interest at admin@autotechnician.co.uk and you'll be the first to know when tickets go on sale.
All our events and assessments this year have been subsidised by our sponsors ACtronics, Delphi Technologies, JLM Lubricants and ZF ProTech, and you can tap into their expertise while you are registering for the assessments by simply clicking the boxes when prompted, or visit their websites for more information. Autotech will deliver a number of online presentations in the coming months, but right now we're here with Andy Crook at Got Boost in South Wales. We'll be talking through a case study to help you hone your diagnostic process. Over to Andy.
Today we're presented with an Audi S3 with a running complaint. The customer dropped the vehicle off with a coolant leak, also suggesting that it stalls every now and again. It doesn't quite idle as smoothly as it once did. There was no performance complaint from the customer. However, he said it's only been doing it ever since he had some work done. Okay, so we've test driven the vehicle. We didn't have to go far. The customer complaint was verified almost immediately. The engine idles. It idles unevenly. The obvious concerns we have at that point was we couldn't get it to replicate the stall. So we brought it into the workshop, and what we're going to do now is we're going to get some fault codes. So we're using the VCDS diagnostic platform, and we've connected it to the vehicle, and we're going to see what fault codes are in there. So first thing to note, there are 9 faults found. We've got control module for exhaust valve 2, mechanical malfunction. Sense for ambient air temperature, malfunction. System voltage too low. Coolant pump, RPM too high. We'll come back to this fault in a second. Then we've got bank 1, camshaft sensor, engine speed sensor, incorrect correlation. And then we've got bank 1, camshaft sensor, engine speed sensor, incorrect correlation 2. Bank 1, camshaft A, intake, retard set point not reached, over advanced, intermittent. Camshaft timing adjustment, bank 1, open circuit. Implausible data received from instrument panel control module. And that's our 9 faults. So if this is presented inside a workshop, what we have to consider is which of these faults most meet or match our symptoms. So a control module for the exhaust flap 2 is unlikely to cause our symptoms, so we're going to move on from that one for a second. The sensor for ambient air temperature malfunction. This is an intermittent fault and also unlikely to cause our running concern. System voltage too low. It's probably a flat battery. We're going to ignore that a second. We can check charging, function and battery if we need to. So one I said we're going to come back to, the coolant pump, RPM too high. This fault code is 17800 in the VCDS or P194 alpha. And it's an interesting fault code because the vehicle's fitted with an electric coolant pump to aid coolant circulation. Now, what could cause the RPM to be too high that matches our customer complaints? Well, we have a coolant leak. Now, if there is no fluid medium to pump against, i.e. the coolant has run down, would the pump speed be increased or decreased if it's running in air rather than in fluid? And the answer is obviously it's going to be faster if it's not pumping against the viscosity of the coolant. So I'm suspecting at this point that fault code will go away now that we've topped up the coolant level. We don't know that, but that's my suspicion. Now the second question is that going to have anything to do with our uneven idle? It's unlikely, but we're not going to rule it out. But that is something that we've noticed. And if you look at the data, it happened at idle. RPM was 759 and the load was 3.9% and the vehicle speed was 0. So that happened at idle. So I'm thinking we're going to move that one on a second because I think that's more to do with the coolant problem than the idle problem. Now, obviously the codes that concern us, or should be concerning us, relate to engine timing. So we've got a camshaft sensor 3 versus engine speed sensor incorrect correlation code, and then we've got camshaft sensor 1, bank 1, camshaft sensor G40 versus engine speed sensor incorrect correlation. So we've got cam and crank codes for both the intake and exhaust bank on this vehicle. We've also got camshaft A, the intake camshaft, has not reached its retard set point as a fault code, P0011, and that's also a concern on this vehicle. And we've also got the camshaft timing adjuster, bank 1, N205 open circuit. Now, have we got cause and effect there, or is that something else? And that's what we'll need to investigate as we go forward. So we've started the vehicle up, and what we're going to do now is we're going to capture some data. With this vehicle, we're going to use something called advanced measuring values using the VCVS. And what you're offered is a long list, which is far too long, of information to look at. So what we need to do is narrow it down. So the items we're interested in are the camshaft sensors. So if we just type camshaft into this box, all the pins related to the camshaft come up. What you can do with this box is you can change the size of it so you can see the full wording. So we want camshaft adjustment bank 1 specified, camshaft adjustment bank 1 actual, camshaft adjustment bank 1 specified on the intake, and then camshaft adjustment bank 1 actual. Then if you move that down, we're going to turbo, and then we're going to look at the data. So we can see the exhaust bank specified is 4 degrees, and the actual is 0 degrees. So we've got around about a 4 degree error on the exhaust camshaft. However, the intake specified is 15 degrees, and you can see the intake camshaft value is changing from somewhere close to, and if you hear the engine right now, it sounds not too bad. However, when it's misbehaving, the error here can be more than 30 degrees. It's obviously worse when cold, because as this vehicle's warming up, this is getting closer and closer to specified. Here's the graph we took when we first started it up. and we can see the error clearly on the intake camshaft is 44 degrees advanced against the desired, which is the yellow line, which is 15. We'll have a look now as it starts to play out. You can see the raw data changing. We're at 30, 40, 43 degrees advanced against a set point of 15. And that is what we're able to see when we look at the graph. So what can we see from the initial data capture? Now, I'm looking at the graph of the data here, and I particularly like graphing data as a medium for looking at problems on vehicles. Wherever possible, I like to graph the data. It gives me a visual representation of what's happening over time, rather than just seeing numbers changing rapidly in front of you, which doesn't give you a lot of time to sort of soak in what the numbers are saying. So graphing data, wherever possible, is really, really useful. So if we have a look, we've got some small changes that we can see between the green and the red. So the green, as we see as it comes along, is stepping up and down as the vehicle is sat there idling, but eventually the green line stabilizes and doesn't change much at all. The blue line remains stable all the way along. The interesting point is the blue line starts high, drops immediately low, tapers up higher, drops again, and then steps all the way up to its maximum value before dropping all the way back and then gradually going. And this cycle repeats over and over. If we were to leave this recording over a longer period of time, we'd see that pattern occur again and again and again. So if we look at what we've got, even if you knew nothing about the systems fitted to the vehicle, you would suspect that the problem lies in the area of the blue line. So the representation for the blue line is what it should be mirroring is the yellow line, which is a straight line all the way across. So where we have a difference between the blue and the yellow, that is the magnitude of the error, if you like. So one is specified, one is actual. Whereas when we look at the red and the green, yes, they're not on top of each other. Ideally, that's what you want to see. You want them to be exactly the same. However, the error is greater at the left of the screen, and then it stays the same all the way along the screen. And the readings at that point were 4 and 15 degrees. So the green line, when it matches the yellow line, they're both at 15 degrees advanced. And the set point for the green line is 4 degrees. So there's around about 11 degree error on that camshaft. However, if we look at the yellow and the blue, we have a maximum, I think, recorded here of about 46 degrees. I'll show you the pointer. At this point here, is around 46 degrees with a set point of 15 degrees. So we notice at this point the idle condition or the idle stabilization is at its worst when these two numbers are furthest apart. So the live data now suggests there is a fault, and the fault is worse on the intake camshaft than it is on the exhaust camshaft. Having established we've got a problem with the camshaft sensor positions against the crankshaft sensor, the next thing to do, the next logical step, is to take a measurement of the actual signals coming from the sensors to the ECU. Now to do that, we need a couple of things. One, we're going to need an oscilloscope to measure the actual signals, and another thing we need is the information to find out where the signals are, which wires those signals are, so we can take the measurement. So I've hooked up my oscilloscope and it's ready to go. What I need to now know is where to take the test. Now, if you're taking a sensor value, which is a reading from the engine that goes back to the ECU, if you want to include the entire circuit, the best place to test that is at the ECU. So we've gained access to the ECU, but what we need to know now is which pin the various sensors are on the ECU to take the reading. So we've used an information system, and this one is all data. We've entered the engine details, and we've narrowed it down to our G40 sensor here, which is a 3-wire sensor. There's a red, a blue, and a black wire going to it. So just by looking at the wiring diagram and learning how to interpret wiring diagrams, we're able to quickly notice that the blue wire is the signal, because it's the only one that goes back to the ECU at this point, and it's on pin 30 at the ECU. So we need to get to the ECU, back probe at pin 30, and what that should then give us is a signal at the cam sensor. So that's what we'll do now. Okay, so we start the engine and we've connected our oscilloscope channel 1 to pin 30 at the ECU, and we've got the resultant waveform on the screen. Now, what I've done is I've set my oscilloscope for 200 millisecond time base to capture 2 rotations of the crankshaft or 1 rotation of the camshaft. I can increase this time base. What I'm looking for here is consistency of the signal, because in live data we've got a report that the time and position is wrong. If we have damage to the reluctor ring or a problem with the signal, that can also give us erroneous information to the ECU. So what we're looking for is conformity of the signal at this point and integrity of the signal. We can do that by increasing the time base. If we go too far, so this is 10 seconds, we're unable to see any real detail. So I like to use around about a second to look at an engine at idle to see a repeating pattern of the camshaft sensor. Having established the camshaft sensor integrity, what we need to do now is check the crankshaft sensor. Obviously, both fault codes relate to the correlation between the cam and the crankshaft sensor. So what we need to do next is look at the crankshaft sensor. So in exactly the same way, we're using some data to establish which pin at the ECU. In this case, it's pin 70. It's a yellow and grey wire. We're going to connect to there on the ECU. We're going to start the engine again. We're going to use exactly the same settings for the second channel on the oscilloscope as we did on the previous one. So we're going to have 10 volts, 200 milliseconds to begin with. And what we're going to do, we're going to start it up and we're going to have a look at the classic cam and crank relationship to see if the crank sensor is good, and also the condition of the reluctor wheel on the engine. Okay, so we've connected up and we started the engine. We've got the resulting waveform. So, looking at the waveform, there doesn't appear to be anything wrong with the crankshaft sensor or the physical condition of the wheel. However, it's difficult to look at it when we're looking at it over such a long period of time. So what we're going to do is we're going to reduce the time base to 100 milliseconds, and then we're going to pause the data and have a look at it frame by frame to see if we can see any abnormalities. One of the powerful features of the Pico is the ability to zoom in at a data capture if required, and then zoom back out immediately. So 100 milliseconds, I'm able to see on this screen the entire capture of that waveform. So I can see the crankshaft has rotated through 360 degrees if there is only one reference to. Okay, so we've paused the data and switched the engine off, and now we're going to look at the values that we've got. Now, on its own, this test is of little value unless you know what you're looking at. So the first thing you need to establish is there any problems with the reluctor ring on the crankshaft? So we happen to know that this is a system that uses 60-2 as its reference. So we need to be able to see 58 teeth with 2 missing every revolution of the engine. So knowing that we've got the start point there, and that's where it repeats itself next. If we count all these little spikes, each one of those represents the sensor passing over a tooth, and there are 58 teeth before it repeats itself, and a gap of 2. So we're happy with the integrity of the signal, and also happy that there's not a mechanical problem with the reluctor ring. Now, it doesn't look that clear on the screen, but we can clear it up simply by adding a filter. Now, you have to be careful when you use a filter. I always start by monitoring a signal with the filter off, just in case noise is the problem. Now, if we were to reduce the bandwidth of a filter to a point where it reduces the signal strength, we are not actually seeing. If we saw that, we may think the fault is with the sensor as opposed to with our measurement. So you have to be careful, and in this case we're using about a 90 kilohertz, that's a 90,000 hertz low pass filter, and that cleans up the signal nicely. We can do the same then on the cam sensor, and the picture appears a little bit clearer. This is useful if we now want to look at where the two camshafts should be relative to each other. Now, this test is often used to prove cam timing. However, it's only useful if you know what it should be. So, although we have the data, we've captured it, we don't know if it's right or wrong. Now, this is where Pico used a waveform library. We're able to select the waveform library, and when we're able to select our vehicle. So, if we go to Audi, and this is an S3. Unfortunately, there's nothing there. We've got the S4 and the S5, but I've got no data for this engine or this model. Can we use any other data? Unfortunately not. So this is one of these occasions where we've done some testing, and without a known good one to compare it to, we can't prove the timing of the engine. With no reference waveform, our cam and crank signals have only one purpose, that is to prove the integrity of the signal and the operation of the sensor. So what controls the cam timing on this engine is an actuator fitted at the end of the crankshaft wheel. So that variates the movement of the camshaft. And what we can do is we can look at the variable valve timing solenoid using the oscilloscope. This is the test that somebody else has done here, and we're going to replicate that test but for our engine next.
Rozwój rynku pojazdów elektrycznych spowodował konieczność prac rozwojowych również nad układem hamulcowym. Pojazd elektryczny to pojazd, który porusza się cicho i nie generuje hałasu pochodzącego z silnika spalinowego. Stąd wewnątrz kabiny jest bardziej komfortowo i cicho. Powoduje to również to, że do kabiny docierają dźwięki również z układu hamulcowego, który jest układem ciernym. Grupa ZF w brandzie TRW wyszła naprzeciw temu wyzwaniu i w ten sposób stworzyliśmy klocki Electric Blue dedykowane samochodom elektrycznym. Klocki Electric Blue spełniają wymagania w zakresie testów pod względem hałasu, wibracji i szkodliwości dla środowiska. Są tak zaprojektowane, by nie generowały hałasu, który mógłby przeszkadzać użytkownikowi pojazdu wewnątrz kabiny. Warto wiedzieć, że grupa ZF posiada klocki, które pokrywają zapotrzebowanie 98% rynku europejskiego, jeżeli chodzi o pojazdy elektryczne.
So we've connected channel 3, or channel C, now to the camshaft actuator, and we can see that we've got a waveform which is switching between battery voltage and ground. So there's no reason electronically, looking at that, why the actuator is not working. However, what we're seeing here is only the command, if you like. You can see we've got a voltage and a switch, but we don't know if anything is actually happening. To do that, we need to look at the current drawn by the solenoid and determine whether or not that's within specification, which we will do next. So, we've added an amp flap to the variable cam timing solenoid, and we're now measuring current alongside voltage to the solenoid, so we can verify the integrity of the actual solenoid itself. We've switched the car off, we've paused the oscilloscope, and what we're going to do now is we're going to analyse the data. So the skill with using any diagnostic equipment is capturing data and then analysing it. The more data you capture, the more reliable your diagnosis. So we've now got cam and crank, we've now got the voltage signal to the actuator, and now we're measuring the current at the actuator. So what we want to look at is what is the peak current, and it's 71 milliamps at the highest point, which if you apply Ohm's law you may think is an issue. However, you have to reference that to the on time of voltage, and it was switched on at that point for 3.64 milliseconds. So the current had 3.64 thousandths of a second to build up in that solenoid before it was switched off again, before it starts to collapse, which is what we're measuring and looking at here. So the on time is as important as the current as it's measured. So if we are shown a simple fault code, P0016, camshaft position sensor G40, engine speed sensor G28, incorrect correlation, has required us to connect the picoscope in 4 different places to measure the signals to and from the engine, as well as the current drawn by the actuator. In doing this, we have proved successfully that the problem on this vehicle is almost certainly mechanical and not electrical. That changing sensors and actuators will not fix this car. This now requires a number of different procedures. You could either strip the covers and check the cam timing physically, or you could change the oil and see if that fixes the situation. If the wrong viscosity oil is used, you may not get correct actuation of the camshaft timing due to the incorrect oil being fitted. This is a fault we've had before, but you won't know until you do it. However, what we have successfully proved is the electrical function of the sensors, the electrical function of the camshaft actuator, as well as the condition of the reluctor ring on both the camshaft and the crankshaft, proving without any doubt this fault is mechanical, not electrical in nature.
As an OE company, Delphi Technologies and Borg Warner are pioneers in propulsion technology. From the latest CO2 reducing combustion enhancements to electrification implementation. The latest government announcement has placed the UK on a clear path to electrification, but there are some challenges ahead. The UK government announced a planned ban on selling electric vehicles which use a combustion engine for propulsion from 2030. From 2035, plug-in hybrid vehicles with a minimum EV range will also be phased out. We know that our goal is fully electrified vehicles and that any hybrid technology is a stopgap, but there are challenges for manufacturers, consumers in the aftermarket for the next 10 to 15 years. One of the first concerns is cost, and this is from all parties. Investments in OEs and R&D is extremely costly, and the moment they are unsure for volumes for this stopgap technology. On the other hand, they have to meet their fleet CO2 targets, and electrification is a key to meeting that goal. This in turn leads to consumer costs. At the moment, many pure EVs have a high purchasing cost, although general maintenance is usually cheaper. When manufacturers have to do the R&D on these vehicles, they have to go from concept to design to manufacturing to production, all of which is a high expense at each cost for a brand new technology. The second is charging, and whether this be charging at home or on the road, charging has a big part to play in the uptake of electric vehicle. The infrastructure is growing with the vehicle park, but they have to grow together, and it's not something that can instantly be switched on. The aftermarket. Us in the aftermarket have to be prepared to do some of the heavy lifting. I mean, these vehicles are going to need servicing, maintaining and repairing, just like any vehicle has in the last 100 years. So for us, although the technology changes, the demand on us remains the same. We're here to service our customer and ensure that vehicles remain on the road. Where are we in terms of the technology? Mild hybrid is on the increase in many brands. It offers an increase to the engine's efficiency at a low cost to both the OE and the consumer. Mild hybrid normally operates in the 12 to 48 volt range, and we're going to look at this a little bit more shortly. Hybrid and plug-in hybrid offer a further enhancement on both efficiency and performance, but this comes at a higher cost. They normally operate in the range of around 200 to 400 volt. Fully electric vehicles offer the most efficiency, and they operate in a region from around 350 to 1000 volts. Traditionally, the higher the voltage, the lower the current, and the lower the current, the less loss of heat. So generally more efficient the higher the voltage. Let's go back to a non-electrified vehicle. This example shows a simple front-wheel drive setup. Components that get the power to the wheels are the engine, the clutch, gearbox, differential and drive shafts. Delphi Technologies and Borg Warner already offer manufacturers an off-the-shelf solution for all types of electrification. These are called a family of drive modules, each with a P designation. The first of these is P0. It's called a BISG, a Belt Integrated Starter Generator. It takes the role of both the alternator and starter motor and houses it in a single unit. It can offer enhanced stop-start functions. You can have an E-turbo as an optional extra, which we'll talk a bit about later. It's easy to integrate and it's cost effective because it's a very simple bolt-on addition for the manufacturer. It doesn't offer E-only driving because it simply belt drives around the crankshaft, and it can only assist that combustion engine at all times. It's traditionally located in a similar location to where the original alternator was, and with a strong belt goes around the crankshaft pulley and can offer assistance to the engine when needed. Now, the second system in the family is called a P1. This system can be used where there is insufficient space where the alternator would be, and it's called an ISG, Integrated Starter Generator. Rather than P0 being located externally, the P1 goes in replacement of the flywheel, and it houses an integrated damper, electric motor, flywheel package. It performs all the same functions of a P0, but because it's directly integrated, no external belt is required. Where things start to get very interesting is when we move to our P2, our on-axis hybrid integration. For those of you who are familiar with Volkswagen's DSG gearbox, when they released the Volkswagen Golf GTE, the Passat GTE and the A3 e-tron, they upgraded their dual clutch gearbox to a tri-clutch DQ400 system. This enabled them to use a dual clutch gearbox and electric motor package, but this was all part of the gearbox. Borg Warner and Delphi Technologies are offering a similar setup, but the ability to house that complete unit and sandwich it between the flywheel and the traditional transmission. It's available for single clutch systems and dual clutch systems alike. As you'll see here, the system sits in between the engine and the transmission, and the traditional alternator pictured here on the left is no longer required. The P2 module can perform all of the functions in one integrated unit. Borg Warner offer the design and manufacturing of all components, including the housing and the motors and all of the controllers and cooling system, and including all of the hydraulic system with all the electronic and hydraulic actuators. This motor offers up to 80 kilowatts of power and instantaneous torque, and because it's integrated directly into the unit, it offers superior packaging. Now within this unit there are 3 clutches as shown here. The orange clutch can bring the engine in and out, and the green and blue clutches offer connection to the 2 different transmissions. The blue friction plate connects with the odd gears, so in a 7-speed transmission this would be gears 1, 3, 5 and 7, and the green clutch pack operates on the even gears, so gears 2, 4 and 6. In the electric only driving mode, we engage the first clutch for first gear, and we can spin the electric motor without spinning the flywheel. therefore operating in completely electric driving. We can then switch over to the even gears as we go through the gearbox. Now interestingly, we can also coast, disengaging all clutches and simply coasting. Surprisingly, the coasting offers the most efficient method of driving. But in the real world, we have traffic conditions and we need to slow down. So the system can have regenerative braking and recharge the battery. If necessary, the engine and motor can work together by engaging the orange clutch and a clutch pack gear. We can also charge the battery, whether that be from regenerative braking or directly from the combustion engine. Now, one of the nice things is that with the P2 system, it can be had both on axis, which we've just seen, or an off axis variant, which is even more suitable for smaller applications where there just isn't a space to manipulate the transmission. This system, the P2 off axis, is also compatible with manual transmissions, providing that electrical enhancement without the need and cost of an automatic transmission. The original P0 went in the orange, the P1 where you can see the red, and the P2, whether it be the on or off axis, located here in the green. The P2 system has an integrated motor, and on the off axis variant has the ability for a single phase connection and single to 3-phase conversion directly within the controller. So you'll notice that we only have 2 wires going from the battery to the electric motor. In the previous P2 on-axis system, this was direct 3-phase, with the conversion being carried out externally. The air conditioning pump is also electronic and is driven directly from the electric motor. Now on the off-axis system, we don't need such a high-powered motor because we have the ability on the back to gear it up using a chain and increase its torque. Traditionally, we would have approximately a 20 kilowatt motor in the off-axis variant. To save on costs and maintenance, we use the same oil as it is used within the engine. So there is a commonality across both, and no specialist oils are required. Via hydraulic actuation, we can bring the electric motor assistance in, we can start the engine, we can carry out all of those functions in a really tight, compact housing. Let's have a look at the driving modes. We can, even with a 48 volt system, we can enable electric only driving. We can also use the system to remotely start the engine, so no external alternator is required. We can switch the system off, potentially at high speed, when the combustion engine can provide direct drive into the differential and straight to the wheels. There are instances when we can use the combustion engine to charge the batteries directly. And of course, we can take the charge from the kinetic energy of the vehicle moving as part of regeneration. We mentioned before that coasting is one of the most efficient drive modes, accelerating up and then coasting rather than accelerating and then instantly regenning. One of the nice things about this system is that we can restart the engine even though the vehicle hasn't come to a complete stop. One of the things that a traditional stop-start system can suffer the most with. The next module in the system is the P3, and this is an integrated motor generator unit. This unit is placed directly inside the differential. So rather than the P2 unit, which is before the transmission, and the power from the P2 has to go through each gear, the P3 has a direct drive to the wheels from the differential. But this of course means that we can drive in electric mode, but we cannot restart the engine because it doesn't have a direct connection to the combustion engine. So if you have a P3 unit, then you require a P0 or P1 module to be able to start and stop the engine in addition to the P3. One thing the P3 does give us is it gives us the ability to drive the road wheels, but it means there are no gearing, so it's a straight one-to-one drive, providing additional smoothness and acceleration. The P4 unit is an e-axle, enabling manufacturers to have all-wheel drive without the transmission connection between the front and the rear. It gives the option for electric-only driving, and as there are no gears, it is smooth transmission, and it has a high torque system. The P4 e-axle has the option for either a single speed connection directly to the wheels or through a 2-speed simple gearbox. It in-houses all of the power electronics and the cooling system, and it allows improved traction through all-wheel drive gearing. We also have the ability for the manufacturer to retain their original all-wheel drive system but integrate the P4 module into the rear differential. It just means that you can increase the launching torque and you can have a much slower take-up for better four-wheel drive traction. The P4 module can also be used in pure electric driving for a pure EV. We have two variants. We have an on and an off axis similar to the variants within the P2, and this really just depends on the packaging and the space within the manufacturer's chassis. Let's have a look inside one of the P4 axles used in pure electric driving, on a traditional EV for example. We house all the power electronics, the cooling systems and all the regulation all within the top unit, meaning that for a manufacturer this is an out of a package solution. The E system is geared so we can achieve a top speed of what the manufacturer gives us. So for example, many EVs are restricted to the sub 100 miles an hour because in normal driving the speeds of that are not normally required. We tailor the gear ratios to match whatever each manufacturer requires for their system. Now we've looked at all of the different technologies, let's have a look at their efficiency improvements when comparing it to a standard ICE vehicle. The term ICE stands for internal combustion engine, and it's being used more frequently as we transition to hybrid, plug-in hybrid and fully electric vehicles. The P0 system offers an up to 10% increase in efficiency when used with a standard hybrid, not plug-in hybrid. The P1 offers similar efficiency because essentially the P0 and P1 offer the same functionality, they're just positioned in different locations. The P2 module can offer up to a 30% improvement, and that can be even higher when used with a plug-in hybrid system, as the P2 offers pure electric driving, the same as our P3 module. Then in theory, the more electric driving, then the more efficient the overall comparison. Our e-axle in the P4 offers the same efficiency, allowing for fully electric driving only mode. Now we mentioned earlier about e-turbos, and it's another way that we can really improve not just the efficiency, but the driving characteristics of the engine. For our heavy duty customers, we can offer an electric turbo where the electric motor is embedded directly into the core of the turbo as seen on screen here. We can adjust the electrical speed of the turbine, and we can have 100% of the power with zero demand on the engine. So we can almost completely eliminate turbo lag. Combining that with a hybrid e-motor gives a pretty efficient system. For our light duty customers, in addition to a 48 volt electric hybrid system with either a P1 to 4 family, we can offer an e-booster in addition to the original mechanical turbocharger. This e-booster offers instant torque response, and because of this we don't have the heat associated with a traditional turbo, really improving instantaneous torque, and that combined with an e-motor makes for a particularly fun driving system. In the first phase, the vehicle and engine are running at low load and a constant speed, and because of that there's enough air going through the system to meet demand. The e-booster is not active. During phase 2, the driver accelerates harder and brings in the e-boost's 48 volt system. That provides additional air and instant torque response for the driver. In phase 3, the turbocharger takes over, providing higher boost pressure than the e-booster can provide, and therefore the e-booster is switched off to conserve on energy. Since the turbo is driven mechanically off the exhaust gases, then it can provide that higher speed, because as the engine increases speed, the exhaust gases increase speed and drive the turbo accordingly. Now, in addition to this additional hybrid system and the e-turbo, we can also offer additional 48 volt components, remembering that the higher the voltage, the lower the current, and normally the less heat loss to each component. We can offer a 48 volt front fans. We can offer a 48 volt heating system for the internal of the car, and this can actually be used in conjunction with the car's original heating system, meaning more comfort for the driver. For a moment, let's concentrate on the different types of hybrid systems. We start off with our series hybrid, and a series hybrid is very much like a range extender. The electric motor is connected to the wheels, and the combustion engine, the ICE, is used to charge the vehicle's batteries. But at no point does the vehicle's combustion engine able to power the wheels directly. The second type is a parallel hybrid, and this in fact probably is in the majority of hybrids on the road. The electric motor can power the wheels, the engine can power the wheels. The engine can also power the motor to charge the batteries. But the key for the difference of a parallel hybrid is the electric motor can either power the wheels or recharge the batteries. It can't do both at the same time. For that, we need a series parallel hybrid. A series parallel hybrid normally consists of two electric motors, one for driving the wheels and another for charging the batteries. That isn't their only use, but it's their most common use. Systems like this are a power split device, similar to that used by Toyota in their hybrid Synergy drive. Then we've got our fully electric system, normally with larger batteries, a DC to AC converter and an AC to DC converter as well, to be able to take power to put it to the wheels, or under regenerative braking to put the kinetic energy back into the battery. We know that the end goal is full electrification, and we as the aftermarket need to be ready for that sooner rather than later. And whilst we allow for the market to evolve, emission reductions still need to be made to our existing ICE technologies. The technicians of today will have to upskill to be able to deal with these ever-evolving systems, whether that be face-to-face training, online learning, or a combination of the two. They're also going to need the correct tools and equipment as the day-to-day jobs change. Whatever it be, Delphi Technologies and Borg Warner have you covered. It's worth also mentioning around the servicing requirements. So with these technologies are great, but what does that mean for us with our day-to-day roles? I want to show you just a few examples of brand-specific requirements when servicing and maintaining either hybrid, plug-in hybrid or electric vehicle. The first example is many electric vehicles require a battery health check on their service. Be sure to check. In this example, this Golf GTE, we can click on the electronic battery within the diagnostic tool and then click on the state of health function which you can run. It then provides a state of health report on the battery, looking at each cell and module within the battery. Don't forget, this is the internal battery management system that's carrying this task out. The diagnostic tool simply runs the routine. Be sure to check out your technical data in terms of your servicing requirements. In this Mercedes, for example, they have a desiccant filter within the battery that has to be replaced at regular intervals. This just removes any of the moisture from the battery. One thing to note that is different is the braking system on these vehicles. We tend to have one of three types of braking systems in a hybrid electric vehicle. The first is no different than any other traditional vehicle, but because the engine might be stopped for extended periods of time, there is no vacuum left in the servo to be able to work effectively. Because of this, the first design, not shown on screen, simply operates an electronic vacuum pump. very similar to what we'd have on a diesel engine that's driven from the camshaft. Instead, we have it driven directly electrically. The second braking system, shown on the right, is what's called a decoupled electromagnetic circuit. And put simply, when you press on the brake pedal, there is a big electric motor, pictured here in blue, pushing back on your foot to simulate the feeling that the driver is actually pressing the brakes. In fact, they're not. When the brake pedal is pressed, a sensor measures the force being pressed and then applies that electronically to the brakes through the hydraulic circuit. The reason for doing this is because we can blend regenerative braking and friction braking together to get the desired function. On the left hand side is a decoupled hydraulic circuit rather than electrical. This actually has two hydraulic circuits within the brake system. When the driver places their foot on the brake pedal, a hydraulic pump, the HAS, that provides pressurized brake fluid back onto the driver's foot to simulate that same feeling. It's the same system used as the electronic, just using fluid. Quite common on Renault Zoe and Nissan ENV 200 vans. One of the things you may be aware of is because of regenerative braking, the physical friction brakes just wear less, and that means a reduced demand on the aftermarket for brake pads and disc replacements. Well, interestingly, what we've found is while the disc's spinning, like you can see on screen now, that because the brakes aren't used as much, the brake pads often can have slight corrosion in their sliders. And because of this, every time the disc spins round and the pad doesn't retract fully, the pad surface just catches the disc very slightly. Now, over 5 or 10,000 or even 20,000 mile, this makes really no difference. But as these electric vehicles get higher in mileage, we begin to find that this constant, essentially kissing of the disc with the brake pad, starts to cause uneven wear on the surface of the disc. This uneven wear is called disc thickness variation, DTV. And whilst more common on a combustion engine which relies purely on its friction brakes, on an electric vehicle the constant catching of the disc over 30, 40, 50,000 and above starts to cause this thickness variation. Now, how does the driver know about this? Well, they actually begin to feel judder. So whilst the friction material of the pad and the friction thickness of the disc are all within specification, the thickness variation issue starts to cause brake judder. I know personally I've replaced brakes on electric cars for this exact issue. The customers complaining of judder. When we've checked the brakes, the actual thickness of most of the materials are perfectly fine. In fact, quite common for a car that's done 60,000 mile to look like the brakes that's done 15,000 mile. But the judder is still there, and of course, correct replacement of the discs fixes the issue. I want to thank you for watching this presentation. I know things are often very different at the moment, but learning and appreciating this new technology, which is coming faster and faster, is the first step to being able to service, maintain and deal with these vehicles like we've dealt with every other vehicle for the past 50 years. Thanks a lot.
Hi everyone, my name's Darren Darling and I'm here today to talk about DPF additives. Are they good? Are they bad? Give some advice on what to use, when to use it, and to also give you some tips on how to stay out of trouble when it comes to DPF repairs. So first of all, as all aware, DPF systems, they are a self-cleaning system. So if you're experiencing DPF problems on a vehicle, it's important that first off you work out why the DPF system has failed. You know, the DPF may be blocked or it may be clean and you may have a sensor fault or a condition not met or whatever. So getting a good process in place and spending time on good vehicles so you can get some good data and understanding of how things work. So if we don't know what good is, we don't know what bad is. So it's something that anybody can introduce in their own workshop by spending time in healthy vehicles, and that'll help you spot things that aren't right on problematic ones. So something we're seeing a lot in our workshop is an upturn and damaged DPFs before we get to look at the car. So it's quite frustrating. It's not good for the customer. So thought this would make a useful video for you and maybe help iron some of them problems out, you know. So just to talk a little bit about in-tank additives, because they are really, really good if used correctly, but they're also the biggest killer of DPFs. So tend to be when they're overdosed or used at the wrong time. So I wanted to share with you some experience, and it means you can go away and whatever brand of additives you're using, you'll be able to do your own research and decide which is the right product for the right time. So obviously we use the JLM range. So first of all, what I'm going to talk about here is, bring this in close, the JLM DPF Regen Plus. Now this product, what I like about JLM, it does what it says on the tin. So this is not an in-tank DPF cleaner. This is to assist regeneration. Now it's important that we understand the differences here, because what this is designed to do, it's an iron-based product, which is, this is how most in-tank DPF additives work. It's there to increase exhaust temperature, so acts as a catalyst. So what happens here is, for example, my Toyota Hilux in the background, we've used this all through lockdown periodically to keep the DPF clean. Now, if you go out and data log this vehicle, what you'll find is you can reach regeneration temperatures when under full load. So if you're going up a hill, full engine load, or if you're overtaking, you will reach full regen temperatures when it's not in regen. So you'll comfortably get into mid 500s degrees with this in the tank. That's what it's designed to do. It's designed to spike your exhaust temperatures up to help naturally burn off any excessive soot. And it's very, very effective at doing that, as are, you know, pretty much any in-tank DPF additive. A lot of people, in my opinion, a lot of companies will brand this as a DPF cleaner, and this is where the problems start, because, you know, JLM advise this should not be used on a blocked DPF. It's not the right way to tackle it, you know. So if you're using any in-tank additives in your own workshops, what I advise doing is pick a vehicle with a DPF on it, you know, nice healthy vehicle. You don't need to do it on one that's got a blocked DPF, because that could potentially be dangerous. So no matter what it says on the tin, whether it calls it a DPF regenerator or a DPF cleaner, then what I would advise is, you know, fuel up the vehicle, go out and do some data logging and look at your exhaust temperatures and get a picture of, you know, what normal is, you know. So pick a road test route, do it on the light load and engine, you know, heavier engine load. So you normally 250 to 300 degrees on average, you know, normal driving, but you will peak a bit higher if you're sort of giving it the beans, you know. So go out and familiarise yourself with that particular vehicle and look at normal exhaust temperatures. So then, no matter, you know, I'm talking about the JLM range here because this is what I use in my own workshop, but for the purpose of this, it's irrelevant what you're using. You know, I know what products do when I pour them in the tank because I've done my own research, you know. So I believe that's important if you're, you know, delivering a service to your customers. If you're pouring something in the tank, you need to know what it does, you know. So what you do there is whatever brand of in-tank additive you're using, pour it in the tank, let it mix in, so maybe leave the vehicle running for 15 minutes or so, and then go and repeat your road test. So go out, do some data logging, and watch your exhaust temperatures. This is really, really important, because if you've got a customer comes in and the DPF's blocked and you're using an in-tank additive, higher, you know, increasing exhaust temperatures to keep a DPF clean is brilliant. But temperature is not your friend on a blocked DPF. So for example, if I can hit mid 500s quite easily on the Hilux, if you then flip it there and say I've been running with a, you know, a boost leak or something that's loaded up the DPF quite badly, and then I introduce into the tank this, you know, I've got soot in there now, I've got this additive trying to raise exhaust temperatures, we've got the vehicle trying to regenerate, also raising exhaust temperatures, which is fine to a point, but if that soot's excessive, then what you find between the soot and this, it starts having its own little party in there, and the ECU loses control, and unfortunately we're starting to see an upturn in damaged DPFs because of this. Another thing that contributes to this is when people are resetting soot loadings. So you've got a garage looks at the vehicle, they put an additive in the tank, and they do, you know, they'll say that they've replaced the DPF to reset the soot counters to get the vehicle out of limp mode. Again, that's a big no-no. Till you've assessed the vehicle and found out what's going wrong, then you shouldn't be rushing to take it out of limp mode. And artificially resetting soot loadings also has an effect on regeneration. It can have an effect on the warm-up phase and things like that, and the length of time that the vehicle will regenerate for, you know. Also has an effect on temperatures, you know. So it's just really important that you're not resetting anything until after your repair, you know. So if you're not sure and a vehicle comes into your workshop and it's been elsewhere before you, then don't rush to take the car out of limp mode. You know, go up the road, have a look at your exhaust temperatures first. That'll alert you to whether someone's used additives beforehand. So even if you're in limp mode, if you're seeing exhaust temperatures, you know, 150 degrees higher than normal, then that's an alarm bell, and you should maybe then interrogate your customer and say, have you used any additives, and, you know, are they still in the tank? Maybe go and fuel the vehicle, you know, fuel the tank up, or drain the fuel out just to work safely, you know. On extremely blocked DPFs, we would address the blockage first and work backwards, because if the pressure is crazy in there, it's difficult to analyse the vehicle and see if you've got any, you know, have you got any boost leaks. Boost leaks you could smoke test obviously, but you know, have you got sticky turbo vanes or EGR function correctly and things like that. It's difficult to monitor if the pressure is crazy. So again, if you thought it was overdosed with additives and the pressures were extremely high, then address that first, get the DPF clean first before going monitoring the vehicle. So that's, you know, a very, very good product when it's used for its correct purpose. So again, whatever you're using, get some in the tank, use the correct dosage. You know, if it says put a can in with 60 litres of fuel, then that's what you should do. Don't put it in with 30 litres of fuel, because then you might get a high temperature or higher than what we would like, you know, and then you're faced with thermal damage or cracked DPF or something like that, you know. So that's a Regen Plus, which is very similar to almost, you know, probably 90% of the additives out there. Very, very, very good for keeping a DPF clean. So as a preventative measure, or if you've done a repair and the customer does a lot of fairly short journeys and would like to keep the DPF clean, then, you know, something along these lines is very, very effective at that, you know. So over the last 6 months, where I've done very little mileage in the Toyota, that product has kept my DPF nice and clean, you know. So very, very good at that. So we'll move on to another product, which is also an in-tank additive. Again, this one's JLM. There are other products out there. The reason I'm using this is because I know these products and I know how they work. So this one there, it's quite simple. It says it on the tin, DPF particulate filter cleaner. Now this one is safe to put in the tank when you have a higher soot loading. So if your DPF's partially blocked, we use this for minor blockages, but this is cerium and platinum based, so this doesn't cause a spike in temperature. It works, you know, on a similar sort of principle as the PSA Eloise system, where it starts to burn off the soot at a lower temperature. So as it's starting to go through the warm-up phase and go into regeneration, you'll find that your pressure in the DPF and the soot loading starts coming down sooner, you know. So you shouldn't see an overall increase in exhaust temperatures with this in, compared with what you would see normally during regeneration. So again, whatever brand you're using, on a healthy vehicle, you should go out on the road, data log it, you know, get comfortable with what you're seeing, and then adding this in there should just look the same, you know. You shouldn't be seeing 100 to 150 degrees higher exhaust temperatures, because that's not how this one works. So whatever brand of product you're using, by doing that, it means it tells you, is this a nice safe additive to put in, because, you know, I've repaired a boost leak or an EGR fault or whatever, and the DPF's only marginally blocked, and is this safe to bring that pressure back into line? So again, doesn't matter what brand it is, doesn't matter whether it's JLM or one or the other. You know, there's plenty other good quality brands. This is just what I choose to use. You know, we have great results, and I trust the product. But that's how I determine in my mind which is the right product for the right job, you know. But like using the right spanner for the right job, really, isn't it, you know? So, so hopefully, you know, that gives you something to think about, because I think it's an overlooked part of people's process, you know, finding out if there's additives in the tank before you start, you know. So customer questioning is key. You know, we have questionnaires that we give out to our customers before we even look at the vehicle, so we can, you know, ask about things like additives and so on. So it's a good little thing to introduce into your process, and it means you're not diving in there, finding a fault, taking the vehicle out of limp mode, resetting your DPF data, and then you go up the road and the DPF melts. And then you call and help from us, or you're tackling it in your own workshop, and you can't fix it now without fitting a new DPF, which, as we all know, is very, very expensive. So it's an increasing problem. So we thought this video would be useful for some of you, you know, just to help think about what you're pouring in the tank, you know. But I can't stress enough, use it at the correct dosage. Amount of times we've seen it where people have put 3 bottles of something that's been on special offer in the supermarket, and then it comes into us and the DPF is melted. So just thought, put this out there, and hopefully, you know, you've found it interesting, and it gives you something to think about when you go into your own workshops and you go and spend some time and you know, go and do some data logging or whatever, and then at least you've got confidence in what product you're using. So okay, thanks for watching. Hope you've found it interesting. Cheers.
We hope you enjoyed the technical presentations and you've learned a thing or two. Thank you very much to Andy at Got Boost, and also our sponsors ACtronics, Delphi Technologies, JLM Lubricants and ZF Protech.
We really hope to see you at a live technical event very soon, but in the meantime, please remember to subscribe to the magazine and also to sign up for the free online assessments at www.autotechnician.co.uk. Take care of yourselves.
Thank you.